Okay, I will talk about work that we did at INRIA in the perception team, let's say for the last 4 or 5 years. And this is, there are many contributors to this work. They are not at all in either alphabetical order or of order of importance, just as they came to my mind. And most of these people left INRIA, and the remaining people are just Xavi, Florence, and myself, I guess on this slide. And then I would like to go through some sensor fusion examples that are well known in science and in engineering. In particular, computer vision scientists are very familiar with what is called RGBD images, which is a combination of standard cameras that provide color with range sensors. And in general, this fusion problem here, it's relatively simple because these two modalities come under the same, let's say, format, like an image that each pixel encodes either color or range. There are other fusion problems that are a little bit more complex, like, for instance, the ones that you can find on a car these days, but also they are available on other devices. And for instance, cars have odometers, inertial sensors, lidars, which are just time of flight systems, GPS, etc. And there are well-known frameworks to fuse this type of data in order to make navigation more precise. There are other sensor fusion problems, however, that I think they still challenge researchers. And I just picked up 2 examples. Vision and touch. Vision and touch is an extremely complex problem because on one side, vision, you have photometric information that conveys, let's say, a global layout of the world, and touch, which is in fact a thermic signal that conveys very local information. And combining the information provided by visual sensors with information provided by touch sensors is extremely difficult. And the other example is the one that I'm going to treat today, which is vision and hearing. And I would like to put my talk in the framework of human-robot communication, of course, because this is one of the things that we are studying in this project. And let me just bring in some perspective, maybe from biological and cognitive sciences. So I would say that in general, vision is present across all the animal species, and it allows animals to build what I would call objective representations of the world. On the other side, speech and language are only present in humans, and they go well beyond objective representations in the sense that they allow to build abstract concepts. This is what in his recent book, Yuval Noah Harari called intersubjective concepts. And this, I think, is very important to understand the role of objective representations against intersubjective representations. An intersubjective representation is something like Barack Obama was the president of the United States. There is no physical representation of this statement. It's just that we all believe that he was the president of the United States. So this is a typical intersubjective concept. In clear, it means that you have to combine, when you do multimodality, you have to combine objective representations with abstract representations. And this is, I think, key to understand how vision and audio will enable in social interaction, whether they happen between humans or between humans and a robot. And understanding exactly and exploiting the complementary roles of these two modalities, I think, is one of the key ingredients of human-robot communication. So I'm repeating again what because I often, when I'm talking about human-robot communication, people want to know what is the difference between human-robot communication and interaction with intelligent devices. And this is a good question. And I would usually I answer in the following way. Systems like Alexa, Google Home, Siri, etc., they perform question and answer dialogue. Okay, who is the president of France? They can answer this. They simply access the Wikipedia or things like that, and then they find the answer. But they cannot answer questions where when the question is related to objective physical, let's say, events or objects that happen in the world. And this is a problem, right? Because this is exactly what we want to solve in our case. And the problem also when you go from human-computer interaction to human-robot interaction is that in the case of, in these cases, in the case when you interact with an intelligent device, the human is in the loop, in the sense that, for instance, if Alexa doesn't hear you very well, then you just know that you have to move closer or to shut down the radio or something like this. And when you have a smartphone in your hands, you know that you have to put this smartphone in a proper position, or you simply quit the room if you want to talk with Siri. So this is to say that the human is in the loop. In human-robot interaction, we don't have the luxury to have such clean speech signals and images of frontal faces. So one key problem is how to perform robot actions that will lead to clean data collection. This is what I call sensory motor learning. And it is not something that we have solved. At least we have not yet completely addressed this problem. And this is something that I think is very important that we should address in spring. And what I'm going to talk about now are the ingredients that the perception team brings into the spring project. So, okay, I think that I already addressed the content of this slide, so I will simply move forward, and I will formulate the problem that I want to talk about, and then I will briefly present one of the basic frameworks that we use, which is variational inference. And then I will present audio-visual tracking, speaker diarization, and visual focus of attention. Okay, so this slide, I will summarize in this slide the basic idea of multiple person audio-visual tracking. So we have visual information in the upper side of the slide. We have audio information on the lower part of the slide, and what I put in the sorry, do you see my my cursor? Do you see my mouse?
Yes.
Okay. So what we have in the middle here are latent variables. So there is a latent variables associated with each one of the persons. And each person is characterized by some kind of trajectory that is necessarily, because we are in a tracking framework, so this trajectory is necessarily a little bit filtered. And basically with each one of the persons you can have many pieces of information, such as the current position, velocity, which are standard, let's say, standard parameters in tracking, but also you can also include the visual appearance of the person, of each person, and also speech information. Okay, so I will talk about all this in this talk. So just to make things clear what we mean by visual observations here, so I assume that I have available a person detector. So these person detectors are now routinely used in computer vision, and basically they provide two things. They provide location. So from a person detector, it's quite easy to predict, let's say, the position of the mouth. So I'm indicating the location of the mouth here. So this is a location in the image plane. But also it's possible to have what I called in the previous slide, a visual appearance, which is basically a photometric description of that person, which will characterize a particular person for a period of time. And let's say that this is this photometric description is a vector that lives in some high-dimensional space. I just randomly said that it's 1000, but it can be anything. So I'm calling the visual observation with a letter V. Similarly, we have audio observation. So here I tried to abstract many years of work and many different approaches, but basically you have to think of audio observations in the following way. We have a device that records sounds, so it has basically two microphones on both sides of the head, and from these microphones we perform some spectral analysis, so that each time frame we get a binaural feature, which I'm representing here, which lives in some high-dimensional space. And what is important to keep in mind that this binaural feature is split into subbands. So I will index each subband by k. And of course, the question is, how do you associate this binaural feature with, for instance, an image? So this is we imagined a few years ago a supervised technique to do this. So basically, this is Antoine, a former PhD student, that basically moves horizontally and vertically a sound source that also has a visual target on it. And for each position in the image, the binaural feature is recorded. Therefore, we have an annotated data set of binaural features with their corresponding sound source positions. And therefore, we can build a mapping from binaural feature space to position space. Okay, so this is what I will call, audio observations are these binaural features. Okay, so let me now put all this into the framework of tracking. So I will start by the very simple linear dynamical system, which is called the Kalman filter. And I will consider in this on this slide a simple example. We have a single person, let's say, a single latent variable that is denoted x at time t. And we have the Kalman filter is characterized by the dynamic model and by an observation model. And this, if you just consider that the additive noise V and W are Gaussian variables, zero-centered Gaussian variables, then it's straightforward to obtain a recursive computation of the posterior distribution. And in the case, so this is called a linear Gaussian model. And the solution for the posterior distribution is tractable. Okay. Now, what happens if I'm trying to extend this simple concept to multiple persons, which basically means multiple latent variables. So now at each time t, or at each frame t, I have to deal with capital N latent variables. So there is one latent variable for each, for example, for each potential speaker in the room. And I have capital L visual observations at time t, and capital K audio observation at time t. Okay, and let me jointly call these observations OT. So there are L plus K such observations. And now clearly I have another problem, because here I assumed that the latent variable xt was observed by a unique observation. This is not the case here anymore, because now I have many possibilities to associate the latent variables x with the observed variables v and a. I have many possibilities, right? And therefore I have to write down these possibilities. And for this I'm using a standard solution in mixture models, which is to introduce discrete latent variables. So a discrete latent variable ztm equals to n means that at time t, observation m is assigned to person n. Okay, so I have to, okay, so this variable, I have to estimate it. It's unknown, right? And it's very important now to understand that in order to make the tracking robust, we also have to somehow to say that one of these observations is bullshit. It cannot be assigned to any of the persons. So this is assigning this observation m to nobody, okay, or to zero. This is very important. So now let me try now to compute, as before, the posterior distribution of x given all the present and past observations. So I get this, so this is done, of course, by marginalization. So I get this integral, okay, over all the continuous latent variable. This is, if we stay with a linear Gaussian model, this is still tractable. However, you can notice that here there is a summation here, and if I make this summation explicit, I come out with a number of components which is exponential in time and in the number of observations. So it means that as time progresses, I get more and more mixture components, and at some point it's completely intractable. So you cannot solve this multiple person multimodal tracking. You cannot solve it exactly. So we need an approximative solution. So a long time ago, we decided to go for variational inference. I'm not going to discuss let's say the advantages of variational inference, which is an approximative technique over other techniques. I'm just selling it as we build it. So the basic idea of the variational inference is to consider the joint distribution of all the latent variables, continuous and discrete. So here I'm making a difference between visual observation assigned to a person and audio observation assigned to a person. So I'm considering the joint probability of these latent variables given all the present and past observations, and this will be this joint distribution will be approximated by a product of posteriors. And this approximation, it turns out that it provides the best factorized estimate of the true posterior in the sense of the Kullback-Leibler divergence. So this is a well-known result. I don't need to prove it in this particular case. And therefore, I can build an unsupervised and it turns out efficient VEM, Variational Expectation Maximization algorithm. So what this algorithm does, it alternates between what is called the E-step expectation. We evaluate the posteriors, and at maximization step, where actually we do some optimization in order to estimate the model parameters. So in this case, the model parameters are the speaker positions, the velocity, and the covariance matrices. And the good news are that all these parameters are all, both the E-step and the M-step are closed-form analytical solutions. So the algorithm is extremely efficient and extremely fast. And as a side effect, I will show you why this algorithm is interesting, because as a side effect, it also provides audio observation to speaker assignments that are useful to do diarization. So I'll show you in a while more details about this. Okay, now I would like to say a few words about our supervised learning of sound source localization algorithm. So it turns out that we published a number of papers on this, and as I said in the previous slide, we have annotated data. However, you should keep in mind the fact that this data, although it has been recorded in a specific room, is room independent, because we are getting rid of the reverberation. We are getting rid of the particular acoustic properties of the room in which the data were recorded. So the data is more or less, let's say, room independent. However, it is robot head dependent. And this is very important in the sense that the localization, the mapping from binaural spectral features to localization depends on the head of the robot with which you do the experiments, because of the shape of the head, the material, the location of the microphones, the number of microphones, etc. So this has to be, supervised learning has to be done again and again anytime you change the properties of the robot head. And another difficulty we have encountered when we did this is the following: that in general, you would like to localize speech sources, speech signals. In the spectral domain, in the short-time Fourier domain, the speech signals are sparse. So this means that not all the frequencies are present, and that it means that this will bias the localization. So what we decided to do is to use different signals at learning and at prediction. So at learning, we use what is called a chip signal. I'm not going to too many details, which is a signal that has a full spectrum in the Fourier domain. And then once we have learned the mapping, then we can predict any kind of sound using, for example, using speech, knowing that there is a limitation, because if there are not enough frequencies that are activated, then the localization is poor. So this is one limitation. So one way to solve this problem is to listen for a longer period of time, like let's say on the order of a quarter of a second. And another important feature of this is that multiple sound sources can be localized by simply applying this method to spectral subbands. And in practice, we use a method that we have developed at INRIA, which is called Gaussian mixture of inverse regression. And the advantage of this Gaussian mixture of inverse regression, first of all, it is because this method allows missing data at prediction. Then we can indeed use this method at learning and use it to compute the predictive distribution. And also it needs a small training set. Okay, so now once we have solved this tracking problem, what about diarization? I think this is something that is very interesting for the project. So now I will introduce an additional variable, which is the speaking status of person N at frame T. So let me call this variable STN that takes values either 0 or 1. And the audiovisual tracker that I just presented, in fact, what it does, it computes probabilities of assigning a spectral subband K to a speaker I. Okay, so how it does this? Basically, it computes the posterior probability that at time t, subband K is assigned to speaker I given the observations. And now I have to decide, of course, this probability is computed for each subband and for each speaker. So now I have to decide to which speaker exactly I'm going to assign that particular subband. So I'm taking the argmax of this posterior over all the speakers, and then I will assign this particular subband to speaker that maximizes this posterior. And therefore, I can easily assign subbands of speech to speakers, knowing that the speakers were already located in the room. Okay, so this is very simple, but it allows overlapping speech to be assigned to different speakers, and this is, I think, quite important. And what are the weaknesses? Large subbands favor good sound source localization, but on the other side, narrow subbands favor separability between simultaneous speech sources. So we have to find a compromise between good localization and good separability. Is there an alternative? Yes, we do have thought of an alternative where, so here in the first part of this slide, S is a variable that is computed afterwards. Once we have computed all the probabilities at all the posteriors at each frame. But it's also possible to treat directly ST as a discrete latent variable in again dynamical system like the one that I just presented. And this means that one has to compute the posterior of ST given the past and present observations. However, this treatment of diarization means that one has to specify the dynamics of the diarization. Basically, the probabilities of ST given ST minus 1. And this is, I think, not easy because you have to, what we did in this paper that I'm citing here, we assumed that the probabilities were independent for each speaker. So that basically means that at time t, if one person speaks, is independent of whether another person spoke at time t minus 1. And clearly this is a limitation. And currently, I must admit that I don't know exactly how to model diarization when there are conditional probabilities in between speakers. So I also want to talk a little bit about visual focus of attention, or who looks where. So this is a purely vision task, that we solve it as a vision task. But I think that this is an example of how we could model interaction between people. And I think that what I would like to investigate in spring is how to combine this visual focus of attention with speech, with diarization, and with language. And I think this is something that is very important. And let me just spend a few minutes with explaining this. So I'm taking here in this an example where we have, let's say, 3 objects of interest: person 1, person 2, and person 3. So what is called visual focus of attention, for instance, person 3 looks at person 1. So the visual focus of attention of person 3 is person 1. The visual focus of attention in this case is a person, but it could be a tabletop, it could be a robot, it could be anything, right? So, however, there is a discrete number of objects that, let's say, attract the attention. And so I will just introduce a few notations. So capital G Tn is the gaze direction of person n at time t. Okay, and I'm making the difference between gaze direction and head orientation. This is very important. So head orientation in this case is noted h at time orientation at time t of person n, and also we need to introduce objects. So x is a location of object k at time t. So in this model, objects can move around. And with these definitions in mind, so let me repeat: G, H, and X are continuous variables that are associated with each one of these continuous variables is associated with a discrete object, a person n or an object k. To this continuous variable, I will add a discrete variable, which is what is called the visual focus. So visual focus, for instance, in this case, I'm taking the example of person 3 that looks at person 1, VT3 equal 1. Okay, the visual focus of number 3 is number 1. Okay, so this is a discrete variable that only takes as values the number of possible objects in the room, or as I said before, 0, which means that someone looks nowhere. It's very important. And let's now look what happens, for instance, when this person looks to a person that is just in front of it. So let's say that in this case, the head orientation is identical to the gaze direction. But if all of a sudden this person turns his or her attention towards this person, then the gaze or the eye direction is different than the head orientation. Okay, and this is what happens in practice. Okay, you cannot consider the head orientation as the direction of gaze. Therefore, one has to treat head orientation as a measurable, as an observation, and gaze as a latent. And the correlation between gaze and head is complex. It has been studied a lot in cognitive science, in psychophysics. And Benoit, who is the author of this paper, came out with a very nice model. And basically, again, here, what we need to do is to compute the joint posterior of the latent, continuous latent, which is gaze, and the discrete latent, which is visual focus of attention, given the observations. So here we're assuming that the head orientation is provided, as well as the location of each object in the scene over time. And therefore here we again have an instance of posterior that contains both continuous and discrete latent variables. And again here, exact inference is intractable. In this case, in this particular case, we proposed an approximate solution that was based on the generalized pseudo-biased order 2 algorithm, which is a well-known algorithm. But in practice, I think that the variational inference is also possible. And this is something that I would really like to address in spring, how to properly combine this concept of visual focus of attention, and especially how a person changes over time his or her visual focus of attention according to various things that happen in the audiovisual scene, and to put this in a framework that takes into account not only low-level information, such as position of objects, but also higher-level information, such as maybe, I don't know, language content or things like that. I think this is something we really need to investigate. Okay, so I'm almost done with my seminar, my talk. Just want to point out that we recorded a data set that is called AV-Diar, like audiovisual diarization, that is available on our website. And this is, I think, a good way to exploit, let's say, algorithms that would analyze, let's say, non-informal gatherings where people who move around, number of people varies over time, people turn their heads, etc. It's quite challenging. This data set comes fully annotated. The location and the trajectory of each person is annotated. The speech activity of each person is annotated over time as well. There is no speech word annotation, but this I don't know if it's worthwhile to do this annotation because the data set is recorded in French. So I don't know if it's relevant to do this. Okay, so just to give you an audiovisual tracking example, so this is just to show you the difference between what this kind of approach offers against things that are, let's say, modern today, like deep learning techniques for tracking. So what offers this approach is that not only that you track, but you have some uncertainty information about what's going on there. And here what I'm showing is that the visual uncertainty is smaller than the audio uncertainty. So here you can see, for instance, that basically here you can see that this person speaks, then there are two persons speaking, two persons speaking, two persons speaking, etc. And what I would like to say also is that it is nice to see here that it's very important to use vision, because detecting 2 or 3 or any number of persons that are appear in the scene is not a problem, because they are spatially well separated. Although in audio, this is a problem because the speech signals are mixed together. So it's very important to, from my point of view, to combine the two modalities. And here, what I'm showing the uncertainty of the dynamics, and you can see that over time, the system maintains quite good knowledge about the presence of the speakers in the room. Okay, so I don't have time to play the videos, and they are not very easy to play over the conferencing system, but I invite you to look to this, to have a look to these videos. Okay, so let me now conclude my talk. So what I'm trying to advocate is that audiovisual machine perception has a strong potential as it combines two complementary sources of information. In fact, these two sources of information have different physical and mathematical properties. I'm not going to go through the list, but clearly they behave differently from a physical point of view, and they live in different mathematical spaces, and they have different mathematical properties. So fusion is not yet completely understood, and this is, I think, is worthwhile to continue to investigate. The multi-person Bayesian tracking that I presented has one big advantage over discriminative learning, in the sense that the parameters are continuously adapted to the data, as opposed to discriminative learning, where the parameters are frozen at training time. And I think this is one advantage of generative tracking. The proposed framework is very flexible to incorporate various supervised or unsupervised data representation models from different modalities. So this, what I'm saying, why I'm saying this is because in the team, in the Spring team, in the Spring partnership, we'll have probably audio processing that is different than what we did. But there will be no difficulty to incorporate other kinds of audio representation into the system. And I would really like to be able to incorporate also more sophisticated visual information. And also, I don't know how language information can be incorporated, but I'm sure that there's a way to do it. And let me just say a final word about the fact that the real and the most difficult stuff, in my opinion, is how to incorporate robot actions into such a model. Okay, how the robot pops into a conversation, how the robot decides that it's its turn to say something. Okay, so this, I would like to finish my talk with this and say that this is something that is very challenging and very difficult, and this is probably something that we should really address in the project, and I'm sure that will be a lot of progress with the various partners that we have in the project. Thank you.